Hello, I'm Bruno Zumbo. I'm professor and distinguished university scholar at the University of British Columbia, and today I'm going to be hosting the second 2023 webinar presentation in the knowledge mobilization efforts that we're doing through the UBC Psychometric Research Webinar Series. The second webinar is entitled Bivariate Analyses, Correlation and Regression using jamovi. This is a three-part series on using jamovi. There'll be more seminars over the course of the next few weeks around analyses using R and jamovi and such, but the first three are dedicated to using the software jamovi, which we would have learned about in the first webinar that was presented and is online available to you. Our topic today, we're going to actually use some of Andy Field's data called Discovering Statistics Using R, and from his book, Discovering Statistics Using R in RStudio, very popular book. And we're going to use the album sales data, which is going to be our criterion variable that we wish to predict. And we're going to do some sort of bivariate analyses. We'll keep it straightforward this time through. And the variables are advertisement budget, attractiveness of the band, sales, number of airplays, etc. And our album sales is, in today's analysis, are going to be the outcome variable, the Y variable. Our predictor is the advertisement budget. We're going to do some basic descriptive statistics. The two variables, the little scatter plots, maybe some loess smooth scatter plots, some correlation and regression today. And so let's go give jamovi a whirl and start working from there. You'll see here that we actually have Andy Field's data here, what we learned at the last webinar, so you can actually take a look at the variables themselves. Adverts is advertising budget in thousands. Units, I suspect this may be pounds, but it doesn't really matter for the sake of our analyses. Sales, the number of plays on the radio, and something called the band image rating, how attractive, how interesting the band is. If you see that the image rating is on an ordered scale, an ordinal categorical scale, ordered categorical scale, or sometimes called ordinal scale, 1 to 10 on that scale there, which is kind of interesting. And if we take a look at some analysis, why don't we actually start right off the bat and let's take a look at some of actually this image data is kind of interesting. Let's take a look at the survey plots here, and let's take the image data, this order data. You can actually see right there, right from the beginning, what does the data look like? Just kind of interesting. You can see that there we can actually click on that and turn those into percentages in that way. I think there's some interesting analyses that you can see here. So most of it is, an overwhelming majority of it, a 10-point scale, is actually, it looks like it's from 6 to 9. Very interesting sort of variable. We can turn it around as well so that we can even have it in this manner here on the x-axis, or we can put it within the plot itself. There's not a lot to see here, except that we sort of see the distribution of it in that manner there. And we can also, another thing that we can do is if we go to exploratory and we do descriptives, and we do this analysis here, so we do basically a frequency plot. We're not going to do means or medians of it at this point, but we can just sort of see it this other way here. Now where's percent of total and the cumulative through there, and you can see that everything from really from a 5 to a 9 captures an overwhelming majority of the data in that way there. We can take a look at a couple of plots if we wish. let's actually go to plots here, and we can do, if we want, a histogram of the data. Right, it's not numeric, of course, so we can actually instead do a bar chart. We'll see our bar chart is there. These are counts. Again, not terribly interesting, but it's a fairly straightforward data set to work from. If we instead do the amount of money spent on advertising, well, that is interesting, because now what we might do is a histogram of the data. We'll see that this is the density on the Y, and we can see the amount of money spent in advertising. And that way here, it's really quite a skewed distribution, so it's all sort of lumped up at the lower end there. We could, if we wanted to, do a QQ plot to see if it's Gaussian, but it certainly isn't. I mean, take a look at that skew. That's not going to be terribly interesting there. We actually are going to ask to label the outliers. We can see, look at those outliers point. It's quite skewed. So there's, most of it is, if you see, is in this range here, right, as we see it in that area. We can also do, right, you can see it's nice. Here's the box plot with the violin around it. We can even get rid of the box plot and just do the violin. But together we can see it in there, and there's some wild data points. Most of the sort of, if you wish, the thickness of the data in this violin plot. And so it's really the, if you think of it as the histogram with on two sides, so it kind of looks like a violin in that sense of it. But you can also put the data in there if we wanted, so you could see where most of the data lay in that area. We can also put in, of course, both the mean, which is the square, and the median there. So you can see it's quite a skewed looking data. I suspect advertising, right, I think let's take a look at sales. If we look at sales, sales is quite different looking now. You see the mean and the median there. They're much closer. So you've got a bit more symmetry, if you wish, in the data, but there is some asymmetric feel to it still. It's a bit more lumped in the middle, as you can see here. So there's actually, and of course it's not Gaussian. This is the standardized residuals. These theoretical quantities, if you wish, what it does is it takes every data point and it says, let's simulate artificially next to the data a z-score. And so we standardize it, or a z-score. And so we then plot the theoretical, which is Gaussian, normally distributed as z, and the standardized residual, which is in a sense this difference there, if you wish. And look at that. You've got some heavy, in the middle, it's kind of nice and sort of, you know, it's got nice properties with the Gaussian distribution, but the tails are clearly not what you see here as well. Even the tails are a little off there. All very exciting stuff. So we can see right off the bat, and I'm going to clear out the data just to keep itself a little bit clearer for us. Let's try, and one of the big things that's important here, because we're interested in the bivariate relationships, and we're interested in really wanting to see if we can understand the variation or predicting album sales, if there were prediction, or understand the variation if this were in more of an explanatory model. But let's take a look at a scatter plot here, and let's take album sales as our outcome variable, and the amount of advertising. And look at that, right off the bat, you can see the scatter plot. What we don't see here is that there's a little bit of darkening, but not a lot. Later, not this webinar, but the next webinar, we'll show you how to do something like a bubble plot. There's some controversy, obviously, around bubble plots, because you want to get a sense of where there is more data. Like, does that point the same as that point? Probably not. Why? Because if you look at the density, in terms of the adverts, that's the density. So more of them are sitting in this area for adverts, right, as we saw before. And for sales, it's kind of sideways. You can see it's bit more symmetric. So it's a bit of an interesting connection to it there. We can instead do the box plots, which are, so this is the median. You can think of the box and whiskers, and you've got some outlying data points up in this area there. We could, if you want, do a linear straight line. So this is if you wish, a regression. It's bivariate, so this it also captures, as I mentioned to some of you sometimes when I discuss about correlation regression, the unfortunate mathematical coincidence that in the simple correlation case, it's unfortunate because it causes a great deal of confusion and consternation. In the early days, in the 50s, 60s, even earlier than that into the 70s, the great advantage was for the simple regression that there is a relationship between the standardized B weight in regression and the correlation coefficient, meaning the standardized B weight in a simple regression is the correlation coefficient. That's been helpful in the past when we were worried about computing, but today it's just mostly a bit of an annoyance and makes things very difficult. This imposes a straight line. It's linear. It's imposing a straight line relationship. But we're really interested more in the scatter plot, the pattern in this sense. Rather than linear, we could do loess kind of smoothing. And if you look at the difference there is a bit of a difference, particularly in this area here. So it kind of flattens out. And this is sort of a more loess smooth regression line, if you wish. Put some standard errors on it. And part of this standard error up here is very wide because there's very little data here. And so that standard error, if you wish, there's not a lot of information, placement of that regression line. So there's a great deal of uncertainty and less so in this area here. So the green is the uncertainty around the loess line. And that's quite an informative, I think it's kind of an informative chart on its own there to take a look at. Does the linear relationship capture it? Well, or is the linear relationship between sales and adverts, if you're going to regress sales onto adverts, depends on where you're looking. I mean, there's a little bit in this lower end. It's unclear whether it's strictly linear. We'd want to take a look at some residuals and such in a bit, but you can begin to get a sense of it by comparing those two, and that's the scatter plot kind of idea. There's a couple other ways of getting these plots. This is we could use JJ plot, which if you remember from the modules from last video, in the modules JJ stat is the, where'd it go here? Right, it's the ggstatplot package. So it's a very strong way of doing so. Let's try it with this and see what the scatter plot looks like there. And I think what we said was the outcome was sales. And I'm trying to say, basically, are we getting bang for our buck in advertising? The correlation coefficient is a Pearson correlation. You could also, what are we doing in here? We can also do, this here is a loess smooth line in the plot through there, which is kind of nice looking. We can also do a non-parametric correlation, which is the Spearman through here, and we can also add a bit more through a ggplot layer in this, where you can see just a slightly different amount of evidence around the outliers and things that we in there. Could we fit a straight line? That's the interesting question we can ask. So if we do the parametric there, and let's see if we can do a straight line regression. Actually, I don't think it allows the straight line for the scatter plot itself. I think the default here is the the loess, if we go and we produce the syntax for ourselves, if you would have seen that last time, so you can see the scatter stats, dependent inverts. There's no grouping variable. It is a fascinating kind of idea. There is actually the Pearson correlation, the T coefficient with its degrees of freedom. There's 200 rows of data, 200 participants, or 200 bands, if you wish. So degrees of freedom for the student t-test of the correlation with 198 degrees of freedom equals 9.98, and you've got, you know, a p. What this is saying is that your p-value has like 18 zeros before the 2. That's certainly less than 0.05, and the confidence interval is actually a 95% confidence interval for this. Pearson correlation is between 0.48 and 0.66, and there's 200 pairs of data in that context there. I'm not going to get into things like the posterior Pearson and such. I think I'm going to stay away from some of those in this context here. Let's see if we can also get, while we're here, the correlation. And so it was adverts and sales. And it's 0.58. There's only one correlation coefficient, not terribly useful here. Yeah, not a terribly useful plot on itself from this point of view. If we go to regression, we can actually get the correlation here, adverts and sales, and we can do the Pearson correlation, which is, right, as we saw before, positive 0.578. We can also, if you want, report the Spearman correlation, if you wanted to, and this is the Spearman in this case here. Is 0.5, and the Spearman makes note of the, so is there a monotonic relationship between these two variables as opposed to a straight line relationship? So we can do the Pearson on its own there in a moment there. All kind of interesting, that point of view. We haven't learned a lot. And we do anticipate there's going to be some correlation between sales and advertising. If not, all the money spent on advertising, if you wish, would if it's not related at all to sales, well, this would be a particularly problematic outcome, a very problematic outcome. Well, not for us, not for someone like me or some of you who buy records, albums, but instead, of course, for record companies and others. So if we're interested in sales as our outcome variable, advertising as our covariate predictor variable, if you want. The model building doesn't have much to add here because we don't really have anything to talk about. Reference levels as for categorical variables. We haven't included any of that in our analyses. Let's take a look, however, at collinearity. Autocorrelation. Collinearity is not relevant. There's only one predictor variable. Normality, residual plots. Let's take a look at the Cook's distance, which is a very powerful tool for looking at influence. We can look at the overall F-test for model fit. We can both, of course, do the ANOVA, and if we want the standardized coefficients, and we can save let's save all of these, the residuals, the predicted values, and Cook's distance as well. What we see here now is that the linear regression, there's the R code, if you wish, as we sort of, eventually maybe segue towards doing some coding in more advanced analyses by working in R code itself. And the correlation, the Pearson linear relationship, 0.578. Not too surprising. The square root of the coefficient of determination, that is capital R versus capital R squared, is 0.578, as expected. The R squared coefficient of determination is 0.335, and it is statistically significant, but we would have known that already because we saw that the correlation coefficient, this is a simple regression model. Here's the ANOVA test. Degrees of freedom is 1 for adverse. Well, there's actually only one predictor variable in the model, right? There's only one predictor variable in the model. So, that degree of freedom is 1. The residual degrees of freedom is 198. Look at the mean square. The F is 99.587, and actually the square root of this is in fact the coefficient there, 9.979. And we can take a look at the coefficients themselves. The intercept is 134.140. That's if there is no advertising, just on the basis of the performance of the music itself. You have $134,000 in return, and then for every dollar in advertising, you get an increase of 0.096, and those are the standard errors. You can see the confidence intervals, and of course they're significant because the confidence intervals themselves do not contain 0, and this is the standardized estimate. The Cook's D, the maximum Cook's D is actually, the ranges from 0 to 0.057, and that means that there isn't a very highly influential data point that's in there. This independence, the autocorrelation test, p-value is 0.9060, that's the Durbin-Watson. And the test for normality, curiously enough, the Shapiro-Wilks, says it's kind of normally distributed, although if you look at the tails, it in fact, these are the residuals being normally distributed, and it seems to be, in fact, from what they can tell there, although I think we're going to see in a few minutes in the residual plots themselves, there may be other assumptions. This plot, which is the plot of the residuals against the fitted value being the model, you'll actually see that there is very little, there's a better sort of a reverse fanning effect here, where there's very little variation in the fitted values of greater than maybe 250,000. And you can see there is some this is now residuals against sales, where sales is the outcome variable. So residuals against Y, and you do see there's a relationship there, and residuals against adverse as well. But this is the big one. You can see that this is like, this is the 0 point here. It's like looking down the line, and you can see that in fact the homogeneity of variance assumption, I think, is probably not as tenable here. The big assumption we worry about is that of independence, the data, the residuals, the error terms are in fact there, and in terms of influence, our maximum influence is 0.057, and typically you see values that are much lower than that for the maximum Cook's distance in that sense there. What I'm going to do, if you'll allow me, is actually delete some of those variables here that created, and we're going to go back into Jamovi, and we're going to rerun the regression that we had before, where sales is the outcome and advertising is the covariate, And really what I'd like to do is let's save the residuals first and foremost. Let's see if we can get that from the analyses. We can, right there. We can now do is actually do a box plot of the residuals to see if there's any outlying values. And so let's start actually doing some descriptive analyses here. We'll take a look at the residuals, we'll do a box plot, and we'll label, and look at that there's actually a fair number of outliers. In fact, there are, in terms of the rows of the data, there are those values there, the first, and you can see there is actually some skew in here where there are actually outliers all at the far end. You actually even can be labeled there. And remember, an outlier is something that lies a certain number of values beyond your interquartile range and such. So it's beyond these whiskers at a certain value. That's a definition of outlier. So we've got some high outlying data. In some senses, that's not too surprising, even if you go to the scatter plot itself. You can see there are some very high values that are out here. Now, what's a residual? Now, it's a straight line, so a residual is something that's far away from the regression line. So you can see that there are some values that are quite far away from the regression line itself. Remember, a residual is far from the regression line itself. If we go back and we take a look at the Cook's D, you'll find that you can also do statistics on the Cook's D, although that's already been produced here. And there's the mean, the median, and the min, and it's the maximum value, the Cook's D. It shows that there isn't very highly influential data points there. Well, I hope this was helpful to you, and I look forward to our next webinar.